Lovely. Well, it's our great pleasure to have as our last talk of this morning, Vidit Nanda from Oxford, who's going to be talking about conormal spaces and Whitney stratifications. Thank you, Vidit.
Thank you so much for the introduction, Phil, and also to both you and Whitney for going through all the trouble of organizing this. I know these things are not straightforward. So yes, the topic is conormal spaces and Whitney stratifications, and you are not required by law to know what either of those things mean. We will go through all of that in the talk. Maybe the only preliminary thing I want to say about this is it's joint work with my partner in geometric crime, Martin Helmer, who is at the Australian National University in Canberra. And this is one of the strangest papers I have ever written in my life. Usually when I write a paper, I'm in absolute love with everything about the topic. It's very exciting in the beginning, and then towards the end, things get a little bit harder. The technical details take a little bit longer, and I just want to get it out. I'm sick of it by the end. This was the opposite. I really did not want to write this paper at the beginning, and by the end of this whole journey, I really enjoyed everything I was doing. So here's a Benjamin Button of papers. Let me tell you why we were working on this. At least from my side, almost all of the motivation, even though persistent homology is not mentioned here, was really, it was inspired very much by multi-parameter persistent homology, and let me explain why. If you just pick an integer n and look at an n by n grid, and on all the integer points in that grid, you just put down a dimension. So there's some function d that's taking ij and giving you a positive integer dij. Then you can ask how many, what are the persistence modules that could possibly fill out, what matrices could you put there? And so if you were doing this in 1D, you could put in any matrix of the right shape and you'd get a perfectly valid persistence module. With higher parameter persistence, you have to make sure all those squares on the screen commute. So there are some non-trivial relations. So you imagine a matrix of unknown entries going up, a matrix of unknown entries going right. When you multiply them, you get some quadratic polynomials in the entries of the two matrices, similarly right and up, and those two have to be equal. So what we have is a real algebraic variety, which is carved out by these homogeneous quadratic polynomials. And even if you try to solve the simplest homogeneous equations like xy equals 0, you get singularities. So these spaces are never nice manifolds. And so one of the things that we like about manifolds is this lovely transitivity property. And I don't know how many people see this in differential geometry, so I'll just go over it sort of maybe quickly. So if you take any 2 points in a connected smooth manifold, then I claim there's a diffeomorphism, sort of the invertible smooth map that takes the first point to the second. And if you really want to sit down and prove this, you first show that this works for the disk. What you need is to fix P at the origin, choose any other Q, and then build a vector field that goes from P to Q, but then decays to 0 outside the boundary. So you can do that because we have nice smooth bump functions. And once you've solved the problem on the disk, if you have a general n, you take a path from P to Q, cover it with balls. By compactness, there's going to be a finite subcover, and then you solve this problem in all the little balls to get from the beginning to the end. So the group theory way of saying this is that the group of diffeomorphisms acts transitively on M. The more video game way of saying this is you take a point and you sort of attack it with all the available diffeomorphisms, you'll eventually grow out all of M. So whichever way is friendlier for you. What's strange about singular spaces is that they're, well, not manifolds, but they are certainly consisting of these smooth manifolds glued together. And we have seen all sorts of examples. So anytime you have a simplicial complex, let's say on these points, so on the left is a 0-dimensional space, on the right there's a 1-dimensional space with all sorts of singularities happening at some of the vertices, and then there are there's a 2-dimensional space, but it's not really a manifold in any good sense. There are spots that don't look like pure k-dimensional Euclidean space for any k. So if you have one of these filtered spaces, then you can easily define a filtered diffeomorphism. So it's a homeomorphism of the whole space that restricts to diffeomorphisms on the manifold pieces if you have this partition. So the goal is to bring this nice transitive diffeomorphism property and keep it so that on every connected component of one of these I-dimensional pieces, we do get the fact that you can attack it with any these filtered diffeomorphisms and get any other point lying in that same connected component. And this property is called equisingularity. So the MIs are, for I less than n, these are supposed to be singular in the space X, but somehow if they're in the same piece, then you want them to be singular in the same way. And the easiest way to see this is with an example. And that example will also tell us why the naive approach does not work to constructing these MI. So this is Whitney's own example. This is called a Whitney cusp. It's sort of a quadratic shape. You can see the smile, and then there's a sheep that goes around and comes back. Now, if you look at this space, maybe the first thing you'd want to do is recognize all the two-dimensional pieces and remove them. And so what's left is one-dimensional, and that's sort of the singular locus. This is itself a manifold. And so you now have a perfectly good stratification. There are three two-dimensional pieces. There are these half open planes sticking out from below the line, and then there's this double-sided horn. So those are the three two-dimensional pieces, and then this line is the one-dimensional piece. The trouble is that this point right in the middle, if you look at a tiny neighborhood of it, it doesn't look like neighborhoods of any other point along that line. So any filtered diffeomorphism is forced to fix that point. And somehow we did not realize that when we were doing this naive partition into manifolds by just looking at 2D pieces, throwing them out, then looking at 1D pieces and throwing them out. So this is the problem of trying to find what are called Whitney stratifications. So let's look at what Whitney's solution to this was. He wanted this equisingularity, and he wanted sufficient conditions on these strata, these manifold pieces that gave us equisingularity. So here is what it means to be a Whitney stratification. If you take any two strata at a point y in one of the strata, so let's call them sigma and tau, and so y is a point in tau, and now keep track of the quantifications because they're going to keep going. So you take a pair of sequences, xi in sigma, yi, and tau, and both must somehow converge to this chosen point y. And then you take the lines between x and y at the ith level and the tangent planes corresponding to the xi on the smooth piece tau. And if there is convergence of the lines to L and the planes to T, then L must lie in T. Now, I don't know about you, but anytime the quantifier depth goes beyond 2, I get lightheaded and I don't want to read anymore. So here's the picture of the problematic point at the Whitney cusp. You take the yellow points that are going horizontally along the singular line, they certainly converge to this problem point, and then you look at the blue points that are living in the two-dimensional strata that also converge, and all the lines you can arrange are vertical, but the tangent plane gets flat. The limiting tangent plane gets flat, so that line is not contained in the plane, and therefore that point could not possibly belong to the 1D stratum, so it has to be separated. And so this is true in general, not just for this example. Condition B implies this equisingularity or transitivity of the filtered diffeomorphism group on each stratum. In fact, it's much stronger than that. You get the same transitivity for any hyperplane slice as well, but I don't want to talk about it. So just like this noble goal of finding sufficient conditions that gave us Whitney stratification, another noble goal is to try and compute Whitney stratifications for, let's say, these algebraic varieties that we're interested in. If I've given you a list of their defining polynomial equations, the kind that we would have for this moduli space of 2D persistence modules with fixed dimension vector. So everything seems to depend on these limiting processes, right? So you have to take these sequences, arbitrary pairs of sequences in two different candidate strata and test whether this limiting line will lie on the limiting plane. And this is clearly algorithmically insane to even attempt. There's too many possible sequence pairs. So this does not look, this formulation in the middle of the slide does not look like it's amenable to any sort of computer calculation. So instead of trying to do any combinatorics or algebra, let's just take a step back and think about the geometry of the situation. So I'm now going to move to complex numbers for the rest of the talk, mostly because I don't know what to do in real algebraic geometry. The complex picture, as usual, is much friendlier. So I'm going to let G, R, and K be the Grassmannian manifold of k-dimensional linear subspaces of complex n space, which is sort of identified with real 2n space. And if we look at the non-singular points of X, this analytic subspace, for the purposes of this talk, just think of it as a variety, a zero set of homogeneous polynomials. There's a subspace of the product of the regular points across the Grassmannian, where you look at pairs of point and plane, if which lie there, if and only if the tangent at the point equals that plane. And when you take the closure, what happens in the x reg direction is that you get all of x. And what happens on the Grassmannian side is that you get all the limiting tangent planes at P. So this is a lovely space called the Nash blow-up of X. It's itself singular, so the word blow-up might be sort of inappropriate, but that's what everyone calls it, so that's what I'm calling it. And you get an obvious projection map down to X. And what's lovely about this is that if you look at the fibers of this projection map, then you'll see all the limiting tangent spaces, even at the singular points. So in this picture, red is not a singular point. So you get only one sort of, you just get the limiting tangent, the tangent itself. And the blue is a singular point with sort of a crossing. And here you see that the fiber has 2 points over it. Unfortunately, the Grassmannian is a fairly complicated object. So if you give me equations for X, I have no hope of getting equations for n of X. So we need something that does this sort of cataloging without being as complicated as the Grassmannian. And that's one of the main topics here. So conormal spaces will do exactly that. So we will mirror the construction of the Nash blowup, but with a simpler object. That simpler object is the dual projective space of all hyperplanes. So n minus 1 dimensional subspaces of n dimensional space. So you take, again, your same projective variety X, and now it lives, because it's a projective variety, lives at Pn, and let Pn star be the dual projective space. Somehow the PNs have become CPNs, but they're the same thing. So the conormal space is the subset of the product, exactly defined like the Nash blowup, but now we're looking at all the hyperplanes, so only n minus 1 dimensional planes that contain your given limiting tangent space at X. And so you take that closure, and as before, you get a projection map called, this time, the conormal map, and the fiber is all hyperplanes that contain a limiting tangent space. So this is different. We're not getting exactly the tangent space, and we're getting this family of hyperplanes that contain it. And the good news is that unlike Nash blowups, I can tell you, if you give me equations for, in fact, any subvariety Y, how to get the fiber. And so with respect to this conormal map. So in particular, if you set Y equals X, then you get equations for all of the conormal space. And the reason I'm talking about conormal space is because there's a beautiful theorem of Lee and Tessier from 1988 that says, if you have a smooth algebraic subspace of X, then the pair consisting of the smooth points of X and Y satisfies condition B, if and only if we have a containment of the defining ideals. So like I said, the ideals are just a list of equations. And we know how to get those. So if the intersection of the conormal spaces of X and Y should be contained in some sort of closure. This closure is not the same as the closure that's defining the conormal space, some ideal closure of kappa X inverse. So if you know what integral closures are, that's what that is. But I will get to that in a second. So I'll define what integral closure is on the next. So this is nice. Let me just bring this theorem back so you have it at the top of the screen. This is very nice because instead of checking these hideous families of sequences for verifying condition B, we've now passed to the much nicer looking algebraic problem of whether ideals, one ideal is sitting inside the other. Unfortunately, I mean, okay, so the good news is, yes, I can give you ideals equations for con x intersect con y and for kappa x inverse y, just using the equations of x and y. But there's a problem. The problem is that the right side is not that ideal that I know equations for. It's its integral closure. And if you pick up one of these books on commutative algebra or algebraic geometry, you will see that the integral closure consists of all solutions to monic polynomials of any arbitrary degree whose coefficients live in the ideal. So here, you know, it's all these crazy equations in a ring, and even for a polynomial ring, basic things that we want to do, like test for this ideal containment. Even if you have all the equations for kappa x inverse y and con x intersect con y, you're not going to get equations or be able to check whether this containment thing that we need in the theorem of Lie and Tessier is satisfied. So obviously, people have decided to start cleaning the street outside as I'm giving my talk. If you cannot hear me, just say something and I'll try and adjust my mic. Okay, so now in order to overcome this problem of having reduced our problem to a nice algebraic problem only to find that the algebraic problem is also a mess, we're going to simplify things and restrict to something we can compute. And these are ideal saturations. And this is sort of the last piece of the puzzle that we need to get, Whitney stratifications algorithmically. So an ideal saturation, so if you have two ideals in a commutative ring R, then the saturation of I by J is this ideal with a hideous notation I colon J infinity, which consists of all R, so that if you multiply R with a product of D things in J, then you'll end up in I. Okay, we're not interested in arbitrary R, we're interested in a commutative polynomial ring. And so in this case, if I and J are homogeneous, then so is the saturation. And there's the reason I want these is that there's a lovely relation between the varieties determined by I, J, and the saturation. So the saturation variety is just the variety generated by I, throw away the variety generated by J, and then take a closure. So these can be computed relatively efficiently using just standard Grosvenor basis algorithms. Unlike integral closures, these are very nice to compute. And so here's the main lemma that's driving much of the work. So if you take a pure dimensional complex projective variety here, pure dimensional just means that there's a top, let's say k-dimensional piece, and everything else is in the boundary of that. And let Y be a non-empty irreducible subvariety. Irreducible just means connected, non-empty means non-empty, and x minus x reg is just all the, it's lying in the singular locus, so it's not in the top stratum. And now you consider the saturation, that mess. So what we've done is we've taken the fiber over the conormal fiber of Y and saturated out this intersection of con x intersect con Y. Then the difference that you get by throwing away the conormal map applied to the variety spanned by J is Zariski dense in Y. So, okay, Zariski dense just means that the complement is some codimension bigger than one piece. So Y reg is almost all of Y prime. You just have to throw out some polynomial bits. So this is the main lemma. Maybe it's not obvious how this is helping us get Whitney stratification. So let's use it in conjunction with the other things we've seen. And here, once again, the lemma has just been reproduced at the top. One of the immediate things you can get from this is that that this fiber, the conormal fiber of the special set Y prime, is exactly the same as the intersection con x intersect con Y. And so if you take this lemma and this particular conclusion, the fact that every ideal is contained in its integral closure by solving a monic equation of degree 1, and the Ley and Tessier formulation for Whitney's condition B, then we have the main result. So if X and Y prime are as written upstairs, so projective variety, and Y prime is given by this, taking the saturation, applying the conormal map, and throwing it out of the regular part of Y, then that pair satisfies condition B. This is a warning, not if and only if. So if all of this is true, then we get condition B. If condition B is true, we don't get all of this, but we don't care. We just want to get a good Whitney stratification. And it doesn't matter if it's not the tightest Whitney stratification possible. Okay, so the upshot of taking all of these detours is that this condition, unlike some of the previous ones, is actually computable in the sense that you can put equations for a variety on the computer and out comes the Whitney stratification. And I want to explain how that happens. But there is Macaulay 2 code out there already. It's available publicly on Martin's website. I'll give you a link to it later. And so when I say computable, I don't mean I could write down pseudocode and stare at it. I mean, we could actually start stratifying small 2D, the space of all small 2D persistence modules with fixed dimension vector. So here are some algorithms. I promised near the beginning of the talk that I would tell you how to get equations for conormal spaces from equations of the underlying variety. So let's do that first. So let's say you have an ideal that generates your pure k-dimensional variety X. Then the conormal space is generated by taking basically the Jacobian matrices. So let me, too much has happened. So you get by looking at the Jacobian matrix, which are derivatives of all the polynomials with respect to the n coordinate variables of the projective space. And then if you write C0 through Cn for the coordinate variables of the dual projective space, stick them right at the top row of your Jacobian and take all n minus k plus 1 by n minus k plus 1 minors. Then you get the conormal space. And so this is because directly from the definition, the limiting tangents are the Jacobian minors, and then taking this determinant basically makes sure that the hyperplanes you're looking at, which are linear combinations of things in the top row, actually contain the minors. So this is quite straightforward. You can do this on a computer. Of course, the number of minors gets large depending on the difference between n and k. So when k is roughly n over 2, this is sort of an annoying computation. Okay, and now there's a subroutine decompose, which is just implementing the three constructions of the lemma. And I'm going to try, okay, and I'm going to try and walk you through some of the things in this routine. So you input projective varieties y and x, and out comes a list of subvarieties of y. And initially in line 1, we're just setting them so that yd is everything, and everything yd minus 1 down through y0 are empty. And now for each piece connected component z of y, this j is precisely the ideal saturation. That k is exactly the conormal projection, and w is what you get when you go back to the variety in the ordinary projective spaces, so the product of projective and dual projective. And so this is it. This is implementing the lemma. And once you have this lemma implemented on a machine, with all of these operations, lines 3 through 7, all of these just require ideal elimination, like Buchberger's algorithm, nothing scarier than that. Once you have this, you are able to just build a recursive routine, very simple. There's only 8 lines here, and even the Macaulay code has only like a few lines in it. And this routine is exactly what will build a Whitney stratification of the input variety X. So here's the setting. 1 and 2 are just computing the regular and singular locus of X. And to compute the singular locus, you just look at the Jacobian determinants of n minus k by n minus k type and throw away the c's at the top, which we had for the. So that's also easy to do. And all the hard work is happening in lines 5 through 8 of this. We're merging two lists. So the existing X with the output of decompose, and then the existing X with the output of a recursive call. And to show that this is, using our lemma, it satisfies the stratification satisfies Whitney's condition B. It's a little bit of work, but it's not so bad. And if you have questions about what it actually takes to do this, I'm happy to talk about them afterwards. So, okay, I've given you pseudocode, but I said this was actually implemented. So what does it look like? Well, first of all, there it is on Martin's website. He wrote all of it. I had nothing to do with the code. So go take a look at it. So we wanted to benchmark this against something else, and it turned out that there's nothing else. I mean, in the sense that there's no existing implementation of anything that has this functionality. You feed it equations, complex projective varieties, and it pops out a Whitney stratification. Fortunately, even though there's nothing implemented, there's one paper we found, quite recent. It's by Din and Yellowneck, I think. It's called Tom isotopy theorem for non-proper maps. So just from a few years ago. And so we implemented their pseudocode, which also produces valid Whitney stratifications. And we tried it out on several examples, and here are the results. So as you can see, their code didn't finish on anything. And I'm including the first line of this input table is the Whitney cusp from the beginning, the simple space. So Martin sent me the numbers when he tried it with their algorithm. It took about 25 gigs of space. It computed the singular locus, so it found the line just fine, but it was still working on finding the point 19 hours later, and then we sort of killed it. And whereas this thing took like, I don't know, 2 megabytes and 0.2 seconds. And which is not to say that there aren't hard examples. So the last line here, it took, I don't know how much 242 seconds is in minutes, but it sounds like a lot. 4 minutes? Yeah, so that one took a while, and it also took like a reasonable amount of memory. And of course, the reason is that even Grosvenor basis calculations are technically double exponential. So you get some bad cases sometimes, but they're extremely rare. These guys are actually used in practice. So let's see. I know we started late and all that, but I still want people to get to lunch in time. But I think there is still some time. So let me say thank you so much. And if you want to see more, there are 3 things about this algorithm that I haven't talked about that I have a slide for right after this. So if you're curious about what those are, ask me a question, but otherwise, I'm happy to end here. Thank you for your attention.
Thank you very much, Vidit. Let's thank Vidit. Do we have any questions for Vidit?